In this video, we work through the 5.5 project. This is at the very end of section 5.5 exercises. Basically, it's about curve sketching and logarithmic differentiation. So we're given this function. It is the absolute value of x raised to the x for x not equal to 0 and 1 when x is equal to 0. It turns out that this function is well-defined for all real numbers and it's continuous at x equals 0. We'll show that. And then we'll compute the first and second derivative and use the first and second derivative to infer relative extrema, points of inflection, the intervals where the function is increasing or decreasing, and the intervals where the graph of the function is concave upward and concave downward. Just looking at this, you might think, okay, I've got absolute value of x raised to the x. Well, if I wanted to, I could split that into two pieces. The absolute value of x, remember, is x whenever x is greater than or equal to 0, because the absolute value of a positive number is just that positive number. So we'll get x to the x when x is greater than 0. And then we know that when x is 0, the function is equal to 1. But the absolute value of x is negative x when x is negative. So this is actually negative x raised to the x when x is less than 0. So with this in mind, we can see that I would expect this function to be continuous. I've just got a positive number raised to a positive power here. And then the base and the exponent are the same for all positive numbers. And then here I've got, where x is a negative number, I've got a positive number raised to sort of the opposite power. Now, for example, if x is, say, -4, we'd be on this branch, right? We have -4, that's the absolute value of -4, which is 4, raised to the -4th power. So we'd have 4 to the -4, which is 1 divided by 4 to the 4th. And I don't remember what that is. It's 16 times 16. I think that's 256. I'm not 100% sure. But yeah, that's 256. So we've got 1 divided by 256 there. So when our x values are negative, these are fractions. We've got some number for the base here. And then if we've got a negative exponent, that's going to be 1 over the same base, which is positive, raised to a positive power. So that is going to tend to be a fraction when that absolute value of x is less, or when the absolute value of x is greater than 1. It might be easier if we actually look at the graph of the absolute value of x. So y equals the absolute value of x looks like this. We know that when x is positive, we just get y equals x. And then when x is negative, well, we take that negative number and we multiply it by -1 to make it positive. And so this is what the absolute value of x looks like. If we are beyond -1 and 1, so that the absolute value of x is greater than 1. So if we're over here or over here, then we're going to have a number that's greater than 1 raised to a power whose absolute value is greater than 1. And those numbers are the same, except they have opposite signs. So we'll have 1 over x to sort of x to the x, or the absolute value of x to the absolute value of x. But both of those numbers are positive, and so this is going to be sort of a larger number. If we are in between -1 and 1, if the absolute value of x is less than 1, then we'll have a proper fraction here. So we'll take that proper fraction when we're on this branch, when x is negative. We'll take that proper fraction, which happens to be negative. We'll multiply it by -1 to make it positive. And then we'll have a proper fraction raised to the same power, but that power will be negative. So let me just give you an example. Let's look at f or x equals -1/2. So I have -1/2 raised to the -1/2 power. And you say, well, what does that mean? We take the absolute value of 1/2, or -1/2, which gives us 1/2. We're raising that to the -1/2 power. Now, whenever you have a fraction raised to a negative power, So say a divided by b to the negative n. That turns out to be b divided by a to the positive n. And we proved that in an earlier video. But my point is that if I want to, I can flip this and change the sign of that exponent, and that's legal. It gives me the same thing. And so what we end up with there is the square root of 2. And what is the square root of 2? Is that about 1.4-ish? I think it is. It's about 1.4. So we see that if we are between -1 and 1, these values, or actually between -1 and 0, we're going to have values that are sort of larger. They're going to be larger than 1. In this video, we discussed the section 5.5 project. This is the last assignment at the end of section 5.5 in the Larson Calculus textbook, 10th edition. Basically, it's about curve sketching, and it's also about logarithmic differentiation because our function is a piecewise function, where one of those pieces or branches involves a function of x raised to the function of x. So it turns out f of x is given to us. It's the absolute value of x raised to the x when x is not equal to 0, and the function is equal to 1 when x equals 0. So we want to sketch this curve. We want to know everything that we possibly can about it. So we're going to talk about the domain. We're going to talk about the range. We can think about that as well. We can talk about where the function is smooth, where it's differentiable. We'll talk about relative extrema. We'll find relative extrema using the first derivative. We'll find points of inflection using the second derivative. And we'll talk about where the graph is concave upward versus concave downward, and where the function is increasing or decreasing. So basically all the typical things that we do with curve sketching, but we've got a piecewise function, and because we've got a function of x raised to the x, differentiation requires logarithmic differentiation. Okay, so we know that that's true. And we also know what y equals the absolute value of x looks like. So y equals the absolute value of x is typically defined in two pieces. We say, well, what is the absolute value of x? Well, the absolute value of x is just equal to x if x is greater than or equal to 0. So we just get y equals x, which looks like that. And then if x were negative, y equals x would look like that, right? Let me say, okay, but what if x is negative? If I want the absolute value of x, I take that negative number and I multiply by -1. So that negative number times -1 is going to give us that positive value that we expect from the absolute value. We're taking all these negative numbers and multiplying by -1. That sort of flips the whole graph above the x-axis. So it'll look like this. So you get that V shape. So y equals x on that side and y equals -x on this side. And that's what our y equals the absolute value of x function looks like. So with that in mind, we can actually add more detail to this. When I have the absolute value of x raised to the x for x not equal to 0, I can think of that in two pieces. When x is positive, the absolute value of x is just x. So this is x to the x when x is greater than 0. It's equal to 1 when x is equal to 0. And when x is negative, we take that negative x value, multiply it by -1 to make it positive. That gives us the absolute value of x, and raise it to the x. So this is our function. And because it's a piecewise function with these two pieces, two branches, or you can think of it alternatively with these 3 branches, we might be interested in continuity. Well, x to the x is going to be well defined all the time. If x is a positive number, taking a positive number and raising it to a positive power, and where the power and the base happen to be the same thing, is going to lead to a bunch of points that actually make sense. So, and we could do that. We could evaluate this function at a few points just to get a sense of what the graph looks like. So let's do that. So if x is 1, f of x is going to be 1 to the 1, which is 1. If x is 2, we get 2 squared, which is 4. If x is 3, we get 3 cubed, which is 27. X is 4, we get 4 to the 4th, which is 16 times 16, which turns out to be 256, and so on. And then we know, we're told that when x is equal to 0, y is equal to 1. So I know I'm not going consistent with this pattern. I'm not just increasing x by 1 now. I'm just going back to x equals 0. So when x is 0, what is y equal to? 1. Then we might also be interested in what happens if x is a negative value. So I think the parts that are most interesting for this are those where the base is a fraction, a proper fraction. So the numerator is less than the denominator. And then also those where the absolute value of x is greater than 1. So I'm taking a number that's larger than 1 and I'm raising it to sort of a larger power, like we did here. Actually, because I think those are the interesting cases, we should probably also look at x equals some number between 0 and 1. So let's look at 1/2. So if x is 1/2, we're going to have 1/2 raised to the 1/2, which is 1 divided by square root of 2. Or if you prefer, square root of 2 over 2. And that's about 0.707, I think. It's one of our familiar function values from trig. So that's what we have when x equals 1/2. When x equals negative 1/2, that might also be interesting. We'll take the absolute value of negative 1/2, which is negative 1/2, which is positive 1/2, and we raise that to the negative 1/2. So this turns out to be 1/2 raised to the negative 1/2, which is the same as 2 raised to the positive 1/2. So we can flip this if we change that sign. It's because a divided by b raised to the negative n turns out to be b divided by a raised to the positive n. We won't derive that here, but we can derive that relatively easily using the fact that 1 divided by x to the n is x to the negative n, and then using our exponent properties. But this is at x equals negative 1/2, the y value on our graph is square root of 2, which is approximately 1.4. And if x equals negative 1, get negative 1 raised to the negative 1, or negative 1, so it's going to make it a positive 1, raised to the negative 1. So we have 1 divided by 1 to the first, which is 1. And when x equals, say, negative 2, we have negative 2. That's the absolute value of negative 2, which is 2, raised to the negative 2. So we end up with 1 divided by 2 squared, which is 1/4, or 0.25. And so we do this, and we can graph the function from here if we want to. What we see is when we're plugging in a negative value, we get the absolute value of that value, which is just the positive version of that, multiplied by negative 1. And then we have that same power, or that x value as the power. This ends up being 1 divided by 3 cubed, which is 1/27. And I don't know what that decimal is, but we could find out what that is approximately. Negative 4, for negative 4, we take the absolute value of that, we get 4, raise it to the negative 4. That's 1 divided by 4 to the 4th, or 1 divided by 256. And I don't know what that is approximately. But we can see just from filling out this table that when our x values are positive, we get these numbers that is relatively large. And when we look at the same x values but negative, we end up with these numbers in the denominator and 1s in the numerator. So instead of 1, 4, 27, and 256, we get 1 divided by 1, 1 divided by 4, 1 divided by 27, 1 divided by 256. And then we say, we're told that when x equals 0, y equals 1. And we say, well, there might be something interesting happening between negative 1 and 1. So let's pick an x value between negative 1 and 1 that's positive, and let's pick an x value between negative 1 and 1 that's negative and see what happens. And we see that those are reciprocals of each other as well. We've got 1 divided by square root of 2 there, which happens to be about 0.727, and then square root of 2 itself, which is about 1.4. So with all of these points, we could graph the function just to get a sense of what's going on. When x equals 0, y equals 1. When x equals 1, y equals 1. When x equals 2, y equals 4. When x equals 3, y is 27, which is way up there. And I'll just write 27 and I'll stay over here not to scale. So our graph roughly looks like that. And then over here on this side, at -1, our x value is 1. At -2, the x value is 1/4. At -3, the x value is 1 divided by 27, so it's tiny and positive. At -4, it's 1 divided by 256. It's very, very tiny and positive, almost 0. So we see there's like something interesting happening here in the middle. But as the absolute value of x goes to -infinity, it looks like the y values on the graph go to 0, because what we end up with is that absolute value, which is just some positive number, raised to the same power, but it's in the denominator because those exponents are initially negative. After we rewrite them using this property, x to some negative power is 1 over x to the same power but positive, we end up with these fractions that are getting tinier and tinier the farther or out we go, the farther we go to the left. As we go to the right, we can see that the base is increasing, the exponents are increasing at the same time, so those y values are getting larger and larger. So it seems to me, just from this graph, that the limit as x goes to -infinity of f of x should be 0. Because I'm never going to get a negative number out of this. I'm always taking the absolute, I'm always taking a negative number, multiplying it by -1 to get the absolute value of that number, so it's positive. And then when I raise it to a negative power, that ends up putting a x to a positive power in the denominator. And that's going to be relatively large. So we see that the y values are getting closer and closer to 0 as x goes to -infinity. What else? As x goes to +infinity, we see the y values just keep increasing. So that is the end behavior. And then something interesting happens here in the vicinity of 0. When x equals -1, when x equals 0, when x equals 1, all the y values are 1. There might be something interesting happening in between. So we'll keep that in mind and compute now the limit of this function as x approaches 0. Now it seems to me that this function is continuous when x is not equal to 0. This seems to be continuous and this seems to be continuous. We don't have to worry about a 0 to the 0 because x equals 0 is ruled out. This is just a positive number raised to a positive power, and this is just a positive number raised to a negative power. Positive number to a positive power gets larger and larger. Positive number to a negative power becomes 1 divided by a positive number to a positive power, and that gets smaller and smaller, getting closer and closer to 0. So these are well defined and continuous for x greater than 0 and x less than 0, but there's still this question about what happens at x equals 0, because if I tried to plug in x equals 0 to this, I'd get 0 to the 0, and you say, wasn't 0 to any power 0? Yes, well, but isn't any number to the 0 power 1? Yes. So is it 0 or is it 1? Or, what is it? It turns out that we're going to allow, or we're going to force our function to be equal to 1 when x equals 0. But we don't know if the function's actually continuous there unless we look at the limit of the function as x approaches 0. So let's look at the limit of this function as x approaches 0 to sort of infer what happens in the vicinity of 0. And again, the reason why we think that's interesting, the reason why we want to do that is because this function is defined in branches. This branch is continuous all the time. And then we say at this one point, we want to force the function to be 1. Like, is that the limit of the function as x approaches 0? Because if it is, then the resulting function is continuous. So let's find out. Let's take the limit as x approaches 0 of f of x. Well, f of x, remember, is the absolute value of x raised to the x when x is not equal to 0. And remember from the beginning of the course, from the beginning of Calculus 1, when we're computing a limit as x approaches a number, we're not actually concerned about what happens at that number. We're concerned as x gets very, very close to that number from the left and from the right, arbitrarily close. We want to get as close as we want to 0, and then we want to see, well, what happens to the y values? If we get as close as we want to 0, what do the y values get arbitrarily close to a number as well? If they do, then that's the limiting value of the function. So we'll say, okay, this is the limit that we're interested in. And it's not obvious. If we substitute in 0, we have a 0 to the 0 indeterminate form. Because we can't be sure if that's 1 or if it's 0 or if the limit does not exist. So one thing that we can do if we've got a 0 to the 0 indeterminate form is we can let y equal the limit that we're interested in. And then we can compute the limit or the natural log of both sides. So I have the natural log of y equals the natural log of this limit. Now the natural log is continuous on its domain, which is all positive numbers. And this is going to be a positive number, because this is a positive number raised to a positive power when x is positive, and this is a positive number raised to a negative power, which is just 1 divided by a positive number to a positive power when x is negative. So either way, this is going to be a positive number. So I'm taking the natural log of a limit. Since the log is continuous on its domain, and its domain includes all of the output values of the absolute value of x raised to the x, we can bring the limit or the natural log inside the limit. The natural log of the limit is the limit of the natural log. And we know this property is true. If I have natural log of a to some power, we can bring that power out front. That's that power times natural log of a. Of course, this is on their common domain. So let's force a to be negative, or a to be positive, excuse me, so that this is well-defined and this is well-defined. With this property in mind, we can bring that x out front. And what we have is the limit as x approaches 0 of x times natural log of the absolute value of x. As x approaches 0, of course, x approaches 0. And as x approaches 0, the natural log of the absolute value of x goes to negative infinity. So this is a negative infinity times 0 indeterminate form. Now, if you're saying to yourself, what does the absolute or natural log of the absolute value of x look like? Well, it looks just like the natural log of x, except it's going to be well-defined when x is positive or when x is negative. So natural log of x looks like this. Now, when x is negative, we just have the reflection of that. We're going to see something that looks like this. And that's also because, or one way you can think about it is that these two branches occur because the absolute value of x is x when x is positive and negative x when x is negative. If I replace x with negative x, and this is a positive number, and we can take the log of that positive number, and that's what we get. So this is what natural log of the absolute value of x looks like. So we can see as we approach 0 from the left and from the right, the natural log of the absolute value of x approaches 0. That red graph is y equals the natural log of the absolute value of x. All right. So we've got a 0 times negative infinity indeterminate form, and you might say, okay, well, how do I handle that? Well, we need to rewrite it so that we can use L'Hopital's rule. So we do what we always do. Instead of multiplying by something that goes to 0, we're going to divide by the reciprocal of it. So I leave the natural log of absolute value of x alone, and then I divide by 1 over x. Because dividing by 1 over x is the same as multiplying by the reciprocal, or multiplying by x. And now this goes to negative infinity, and as x approaches 0, from the left and from the right, 1 over x approaches in negative infinity from the left and positive infinity from the right. Just to remind us what that looks like. Y equals 1 over x looks like this, roughly. As we approach 0 from the right, the y values go to infinity. As we approach 0 from the left, the y values go to negative infinity. So this is an infinity or a negative infinity divided by plus or minus infinity indeterminate form. And since that's the case, we can use L'Hopital's rule. So L'Hopital's rule says if you have a 0 over 0 indeterminate form or an infinity over infinity indeterminate form, and then of course you can adjust the signs. then the limit as x approaches that constant of f of x divided by g of x is the limit as x approaches the same constant of f prime divided by g prime. So basically you just take the derivative of the numerator and denominator and take the limit of that instead. The derivative of natural log of x is 1 over x. And the derivative of 1 over x is, well, let's write it out. Derivative of 1 over x is the derivative of x to the negative 1, because we can say 1 over x to the first is x to the same power but negative. We flip the sign. And then when we use our power rule to compute the derivative, we end up with a negative x to the negative 2. And remember, x to a negative power is 1 over x to the same power but positive. So this is just a bunch of algebra, just exponent properties. Got 1 over x divided by negative 1 divided by x squared. And then dividing by a fraction is the same as multiplying by the reciprocal. So we'll multiply by negative x squared divided by 1. The x's reduce, and we still have a negative x there. And the limit as x approaches 0 of negative x is 0. So, okay, well, what does that mean? Well, it just means that the natural log of y, where y was actually the limit that we were interested in, is 0. So if the natural log of y is 0, then y is e to the 0, which is 1. Or in other words, the limit as x approaches 0 of the absolute value of x raised to the x is 1. Now, this is actually our function value. And this is actually the function value as well at x equals 0. So this is another way of saying this is to say that the limit as x approaches 0 of f of x equals f of 0. And since the limit of the function and the function value at that x value are the same, we say that the function is continuous there. In other words, this 0 to the 0 expression is an indeterminate form. We might not be sure what happens to the graph there, but we were able to compute the limit, and we're able to say that the limit as x approaches 0 of this function is equal to 1. So even if this function is undefined there, the graph has a hole in it at x equals 0, y equals 1. But since we define our piecewise function in this way, where it's equal to this when x is not equal to 0, and it's equal to 1 when x equals 0, this actually says the limit as x approaches 0 is actually the function value there. So the function is continuous. And that means we could draw the whole thing without picking up our pencil. So now we know the function is continuous at 0, and it was continuous for all the other real numbers. So the function is continuous for all real numbers. It's continuous on its domain. And the domain of f is all real numbers. Okay, so now we know that. We know the function kind of looks like this. We know it has these 3 pieces, or you can think of it as having 2 pieces. You just remember you're computing that absolute value, which you can think of in 2 pieces. And we know that the function's end behavior is given by this. As x goes to negative infinity, the y values approach 0. As x goes to positive infinity, the y values approach infinity. And the function's continuous at 0. The function value is 1. So I'm not sure what happens in the vicinity of 1, but I know that, or in the vicinity of 0, but I know the graph is going to cross through this point and this point and this point. And say, okay, it passes through all these points. It looks like the range is all positive numbers. And I think that makes sense because of what we have here when x is negative, and then what happens is x is when x is positive. So maybe we should write that down as well. We'll say since the absolute value of x is always greater than 0, x to the x is always positive. So f has a range of 0 to infinity. And I say 0 to infinity, you might say, how do you know it approaches 0? It's because those fractions at 1 over negative x raised to the x as x gets large and negative, or or 1 over negative x raised to the negative x, as x gets very, very large and negative, is 1 over a positive number raised to this a positive power, and the base and the exponent are the same. So again, just like we saw here, these fractions get smaller and smaller. They get closer and closer to 0 as the absolute value of x approaches infinity. Well, as x approaches negative infinity, let's say that. Okay, so we know the domain, we know the range, and now we might be interested in the derivative of the function. So let's compute the derivative and use the derivative to find any points of inflection and any intervals where the function might be increasing or decreasing. So we want f prime. And f prime is going to be the derivative with respect to x of x to the x. You might say, I don't know how to do that. Excuse me, not the x to the x. Let's say the absolute value of x to the x. Well, we can compute that derivative using logarithmic differentiation. So let's let y equal the absolute value of x raised to the x. Then let's compute the natural log of both sides. And then because of our property natural log of a to the n is n times natural log of a, we can bring that x out front. But this tells us that natural log of y is equal to x times natural log of the absolute value of x. All right, so, and y is a positive number, so the natural log of y is well-defined. This is the log of a positive number, which is well-defined. And x can be any number between negative infinity and infinity. And that's fine, because we're taking the log of y has a range of negative infinity to infinity. So it looks like everything is fine, everything is well-defined. We've taken the log of both sides, and now we're trying to find dy dx. If y is equal to this, what is the derivative of y with respect to x? Well, I can compute the derivative using implicit differentiation now. So we'll differentiate both sides with respect to x, remembering that y is actually a function of x. So if I'm taking the derivative of log of a function of x, I get 1 divided by that function. If you want, you can write y of x just to make it a little bit more explicit, times the derivative of the inside by the chain rule. And then this is a product. We've got the derivative of the first function times the second function. And according to the product rule, the derivative of a product is the derivative of the first, which is 1, times the second, undifferentiated, plus the derivative of the second, which is 1 over x, times the first, undifferentiated. And x times 1 over x is 1, of course, provided that x is not equal to 0. So dy dx equals natural log of the absolute value of x plus 1 times y. But remember what y was. Y is the absolute value of x raised to the x. So dy dx is this. And if y is also known as f of x, we could call this f prime of x, same thing. So that's our first derivative. And the question is, okay, when is that derivative equal to 0? Well, this exponential expression is never equal to 0, as we've discussed. The range is 0 to infinity, and we're never getting a 0 out of that. This is never 0, but this factor could be 0. So we'll set this equal to 0 and solve for x to find potential relative extrema of the function. We'll say that means that function is 0 since this absolute value of x to the x is always positive. And then solving this for x, we have natural log of the absolute value of x is -1. Exponentiate to get rid of the logarithm. So you have the absolute value of x is 1 divided by e. Oh, goodness. That's weird. I was writing that whole time and you couldn't see anything. So I said f prime is equal to this. And f prime is 0 when this expression is equal to 0. I've got this times this equals 0. So that means either the first factor is 0 or the second factor is 0. Now, in our case, the second factor is never 0. The second factor is always positive. So this expression has to be 0. Now we just solve this expression or solve this equation where we have this first expression set equal to 0. We solve it for x. We do that by subtracting 1 from both sides, exponentiating to get rid of the logarithm. And then we've got the absolute value of x equals a positive number. That means x is equal to plus or minus that number. Now, to figure out whether our original function is increasing or decreasing, we need to make a sign chart for f prime. So we'll create a sign chart. We'll find the sign of f prime on all the intervals that are defined by the critical values of f. Critical values are x values where the original functions, or where f prime is either 0 or the derivative itself is undefined. So these are both critical values. And this expression is undefined at x equals 0, and this expression is undefined at x equals 0. Now, technically, f prime is undefined at x equals 0, but x equals 0 is in the domain because we defined f to be equal to 1 at x equals 0. So x equals 0 is also a critical value. And that's because f of 0 is well defined. And f prime of 0, or f prime, let's say, is undefined at 0. So here are our critical values. We've got 0, we've got negative 1 over e, and positive 1 over e. We've got to put those on the number line in the right order, negative, 0, then the positive. And we're interested in the sign of this expression. We said, well, the absolute value of x to the x is always positive. Positive there, and there, and there, and there, and all 4 of those intervals. Well, what about the natural log of the absolute value of x plus 1? Well, let's look at that. Natural log of the absolute value of x, we said it looks kind of like this. Oops, I'm sorry, I didn't do a very good job with that. Let me try to graph that again. When x equals 1, y equals 0. And then it has this basic shape. When x equals e, that's about 2.7-ish. Y is equal to 1, because the natural log of e is a question. You say e to what power is e? It's e to the first power. And so that's what y equals the natural log of x looks like. And y equals the natural log of the absolute value of x looks the same. But it's reflected. It's reflected on the other side of the y-axis. So when x equals -1, the natural log of the absolute value of -1 is the natural log of 1, and the natural log of 1 is 0, so we still get a 0 there. And then when x equals -e, but a negative 2.7-ish, the y value is 1. Okay, so that's y equals the absolute value of x, or excuse me, natural log of the absolute value of x. So well, what does natural log of the absolute value of x plus 1 look like? Just take the entire graph and move it up 1 unit. So this point, which was at -e1, is now at -e2. This point, which was at -1, 0, is now at -1, 1. This point goes up 1 unit. This point goes up 1 unit. And basically what we're going to see is this. So this is y equals the natural log of the absolute value of x plus 1. You would say, well, when is that function 0? Well, we know that function is 0 at x equals plus or minus 1 divided by e. So this is negative 1 divided by e and 0. And this point is positive 1 divided by e and 0. So, okay, so now that I know what that graph looks like, what is the sign of natural log of x plus 1 on each of these 4 intervals? Well, if I want the sign of that, all I have to do is look at the y values on this blue graph. Ignore the black graph. That was what I used to sketch the blue graph. I just took y equals the natural log of x, or the natural log of the absolute value of x, which we knew what that looked like, and we just shifted it up 1 unit. Our focus is on this blue graph. Say, okay, if we're to the left of negative 1 over e, what are the y values? Well, they're all positive, right? If we're to the left of that point, the y values are all above, or the graph is above the x-axis, so the function is positive there. So we're gonna have a positive sign there. And then similarly on the other side, if x is greater than 1 over e, our y values are positive there. We get positive numbers there. And then what if we're between negative 1 over e and 0? The y values are negative. What if we're between 0 and 1 over e? The y values are also negative. So this is negative and a negative. So f prime is a positive times a positive on this interval, which makes it positive. It's a positive times a negative on that interval, which makes it negative. And it's a positive times a negative, which makes it negative. And a positive times a positive, which makes it positive. So you say, okay, well, what does that mean for us? Well, f prime is 0 at negative 1 over e and positive 1 over e. So that means we're going to have relative extrema there. And since the graph goes from increasing to having a 0 slope to decreasing, and then at that point and decreasing to having a 0 slope to increasing, we've got a relative max at negative 1 over e and a relative min at positive 1 over e due to the first derivative test. Now, this tells us that the function is decreasing on this interval and decreasing on that interval. So f prime doesn't change signs. And then we're not really sure what happens to f prime at 0. We just know that it's undefined at x equals 0. And you might say, okay, well, what is its limiting value as x approaches 0? Well, we know this function approaches 1 as x approaches 0, because we already computed that limit as x approaches 0 of this function. And then as x approaches 0, the natural log of x plus 1, or the natural log of the absolute value of x approaches negative infinity. So we get negative infinity plus 1, so it's going to be a large negative number times something that's approaching 1. So this function f prime is going to negative infinity because this is a large negative number plus 1, which is just a large negative number times 1. So let's state that for ourselves. The limit as x approaches 0 of f prime of x. The limit as x approaches 0 of the absolute value of x to the x times the natural log of x plus 1. And if you want, you can also think of this graphically. We've just got something that's approaching 1 times a function that is going to negative infinity. And we can see that as x goes to negative infinity, or as x goes to 0, from the right and the left, the blue function is approaching negative infinity. Since this is going to negative infinity, the function is going to negative infinity as x approaches 0. So f prime of 0 is undefined. But if it were defined, it'd be going to negative infinity. So I think that means we have a vertical tangent line there. I think that's correct. Maybe I'm wrong. Actually, I think there might be a little problem with my logic here. I think if the limit definition of f prime of x gives us a limit that is either positive or negative infinity. Then we can infer that f has a vertical tangent line at that x value. That does not, but if we're taking the limit of f prime, we have to be careful because f prime is actually a limit itself. So maybe we should just look at the limit definition before we infer this. I think that this is true, but this is not why it's true. So I want to check my own logic and make sure we actually look at the limit definition of f prime. So the limit definition of f prime is, let's take the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. And actually, we're interested in f prime at 0, right? So maybe rather than using this definition, we could use that. It might be easier to use this one. Let's look at the derivative at 0. So we'll take the limit as x approaches 0 of f of x minus f of 0 divided by x minus 0. And if we're not actually at 0, f of x is the absolute value of x raised to the x. F of 0 is equal to 1. And we're dividing all of that by x. That is the definition of f prime at 0. Well, we can see right away that this is a 0 divided by 0 indeterminate form. As x approaches 0, we decided, or we computed the limit earlier, this function approaches 1. So we've got 1 minus 1, which is 0, divided by something that's going to 0. They say, okay, if I've got a 0 over 0 indeterminate form, let's use L'Hopital's rule to compute that derivative, or excuse me, to compute that limit. We take the derivative of the numerator, and we've already computed that. That's this. And we divide by the derivative of the denominator, which is 1. We said, well, what's the limit of this as x approaches 0? We said that this goes to 1, this goes to negative infinity, and then we add 1. So we have a large negative number times 1, so we get negative infinity. So yeah, actually f prime of 0 is negative infinity. So the graph of f has a vertical tangent line. So the slope is not well defined, but not when we think of y as a function of x. If we think of x as a function of y, turns out that the derivative of x with respect to y is 0. This is just sort of turn your head sideways, and then the slope is 0. Vertical tangent line at x equals 0. All right. So technically that is why the graph has a vertical tangent line. I just said, let's compute the limit as x approaches 0 of f prime. And we got the same value, but we really should use the limit definition to see what happens to that derivative value at a particular value of x. Okay. What else? So we know we've got a relative extrema. We know we have a vertical tangent line at x equals 0, and the function goes from decreasing to having an undefined slope, then to decreasing again. So let's find the relative extrema. We know we have a maximum at negative 1 over e and a minimum at positive 1 over e. So let's find those function values. So this is, well, since we're on that negative branch, we take the absolute value of that and we raise it to the x power. Well, the absolute value of negative 1 over e is positive 1 divided by e. And then we can flip that. So it's actually e raised to the 1 over e power. I don't actually know what that is. That's about 2.7 raised to something a little bit larger than 1/3. That is a relative max by the first derivative test. And then f evaluated at 1 over e is the absolute value of 1 over e, which is 1 over e raised to the 1 over e. So you end up with 1 divided by e to the 1 over e. And I don't know what that is. So we see that these are reciprocals of each other. I don't know what that value is. But we can use Desmos to find that. That is going to be a relative min by the first derivative test. Now let me use my calculator to figure out what those values are. So using a calculator, I found that that number is approximately 1.44 and that number is approximately 0.69. And I guess I should have looked at this 1 divided by e. I think it said 1 divided by e was about 0.36. Yes, that one divided by e is approximately 0.37 if I round to that second decimal place. Okay, so we know that at about x equals positive 0.37 and x equals negative 0.37, the corresponding y values are 1.44 and 0.69. So let's graph those points. Then so much computation. Oops. So we said at negative 0.37, the y value is 1.44. And at positive 0.37, the y value is 0.69. That's a relative max. That one's a relative min. Right? Relative max at negative 1 over e. Relative min at positive 1 over e. And we've got a vertical tangent line at 0. So I think my graph should look like this. All right, so roughly. And let's write down the intervals where the function is increasing and decreasing. From our sign chart, we can see that the function is increasing on a negative infinity and a negative 1 over e, and increasing on 1 over e to infinity. And it's decreasing on negative 1 over e to 0, and decreasing again on 0 to 1 over e. Let me look at my graph, my picture. That what it looks like? Increasing until we get here, then decreasing, then has an undefined slope and then continues to decrease, and then it goes on to infinity. Okay, cool. All right. So we know where the function's increasing and decreasing. We have those relative extrema, and the graph is consistent with that. Let's look at the second derivative to find points of inflection. The second derivative is just the derivative of the first derivative. We want to find that second derivative. We will use the product rule again. This is our first function, and this is our second function. So we have the derivative of the first, which is actually this. Let's write it down. Because the first function is actually our original function y, times the second function. So I'm multiplying by an extra factor of natural log of the absolute value of x plus 1. So I'll just square that. It's derivative of the first times the second, plus the derivative of the second, which is 1 over x, plus 0, times the first, undifferentiated. And so I look at that expression and I say, well, what do those two terms or those expressions are separated by a plus sign? what do those have in common? Well, they both have that absolute value of x raised to the x power. So let's factor that out. And then we say to ourselves, this times what will give us this expression? Well, it's just that natural log of the absolute value of x plus 1 quantity squared. And then we say this times what will give us this expression? Well, it's just the 1 over x, right? And if you want to, you can get a common denominator. So multiply this one by x over x because this has an x in the denominator. And then you can add the numerators. So we'll have the absolute value of x to the x times x times the absolute or natural log of the absolute value of x plus 1 quantity squared plus 1. All of that is divided by x. We can see right away that f double prime is undefined when x equals 0. And we know that this is always positive. So whenever it's defined, it's positive, right? So we've got a positive number divided by something that can't be 0. So let's write that down. F double prime is undefined at x equals 0. And f double prime would be 0 when this expression in the numerator is 0. And say, well, when is that 0? I'm like, I don't know, actually. It's really hard to figure that out. Typically, I would try to solve for x. But if I try to get x by itself, I mean, what could we find? We'll find the natural log of absolute value of x plus 1, quantity squared equals -1 divided by x. Say, I still don't know when that's 0. You could, if you wanted to, you could graph this function and graph this function and find the x values where they cross, right? Find the x values where the y values on this function are equal to the y values on that function. So you'd just be looking for points of intersection. You find the x coordinates. But it's easier to just graph this function and say, well, what does that function look like? When is that function equal to 0? Or in other words, if I look at the graph of this function, when does it cross the x-axis? Because on the x-axis, y equals 0. Let's do that. If I wanted to try to get x by itself sort of explicitly, just solving for x, it would be difficult to do. Because if we square this, we end up with a natural log squared plus 2 times the natural log of the absolute value of x plus 1 equals this -1 over x. And if I try to get rid of the logarithm, I'm going to have exponentials everywhere. And if I try to solve for this x, I'm still getting this x in terms of a logarithm of x. So I'm just really not able to get x by itself. So I will use a graphing calculator to find the 0 of this. And then once we have that graph of f double prime on our screen, we can use the graph of f double prime to infer the intervals where f is, the original function f is concave upward or concave downward. So we have f double prime, we want to know when it's 0, and we know that it's undefined at 0. So we will just graph f double prime and see, look for any x values where this function happens to be 0. So this is f double prime. This is use parentheses around the argument of natural log. So it wants parentheses around that absolute value. And this is what it looks like. It's kind of a pretty graph, isn't it? Zoom out a little bit. We see that f double prime has a minimum value here. That's going to be when the third derivative is 0, right? F double prime has a maximum there. That's when the third derivative is 0. But f double prime is positive, it looks like, on the interval from -infinity to this x value, which is -1. And then it's negative from -1 to 0. And then it looks like it's positive from 0 to infinity. That's what I would guess. Oops, we keep zooming out. It's just, It's very, very steep over here. Like, does it have an asymptote? I don't know. But that's what our graph looks like. So we said when is it 0? It's 0 at x equals -1. So I'm going to make a little sign chart on my paper. And we said, based on that graph that we just looked at, on this interval from -infinity to -1, so this to the right of -1, or excuse me, left of -1, it looks like the y values are all positive. So we'll have positive values here. And then between -1 and 0, we see the y values on the graph of f double prime are negative. And then let's move this over here. To the right of 0, when x is greater than 0, the y values are all positive. So this tells us that the graph of f is concave upward on -infinity to -1 and 0 to infinity, and concave downward on the interval from -1 to 0. Now, any x coordinate or any x value on the original graph, where the graph goes from concave upward to concave downward or concave downward to concave upward, is considered a point of inflection. Not any x coordinate, excuse me. Those x values are the x coordinates of a point of inflection. A point of inflection actually is an xy pair. So if we want to find the points of inflection now, we would just evaluate f at -1 and evaluate f at 0. Well, f at -1 was the absolute value of -1 raised to the -1. So that's 1 to the -1, which is 1 divided by 1 to the first, which is 1. And so that tells us that x equals -1, y equals 1 is a point of inflection. And then our function was defined at 0 to be 1 by that second branch of the piecewise function. So that means x equals 0, y equals 1 is a point of inflection as well. All right. So let's look at our graph. Work from a different problem. Let me find it. This is our graph. So this point is a point of inflection. X equals -1, y equals 1. And then this point is a point of inflection. X equals 0, y equals 1. Then we had a relative max at -1 over e, a relative min at +1 over e. And we're told that the graph is concave upward until we get to -1, then it's concave downward between -1 and 0, and then it's concave upward for the rest of the time. And that's consistent with our picture. And we saw also from our sign chart, the function was increasing until we get to -1 over e, then it was decreasing until we get to 0, and then it was decreasing again until we get to +1 over e. And then it was increasing from +1 over e to infinity. So I think this graph is right. Let's look at Desmos. We'll use Desmos to graph this now and confirm some of our calculations. Now, pretty much everything that we've discussed could have been done on Desmos, but I wanted us to make sure that we actually could graph the function by hand without using the graphing calculator to do all the heavy lifting. I've actually written up our section project in Desmos on this particular page. So f was defined as a piecewise function. I couldn't actually figure out how to use Desmos's piecewise function notation, or I actually chose not to. So I have actually defined the two pieces myself. I called f sub 1, that first piece, So I want our function to be absolute value of x raised to the x when x is either greater than 0 or less than 0. So the graph looks like that. It's very pretty. And then at x equals 0, we want the function value to be 1. So I did that. And then I added that point to the graph. And I made it purple because I knew it was going to be a point of inflection. So we have that. And then we said this function is well-defined for all real numbers for the reasons that we've already discussed. When x is negative, this ends up being a tiny positive fraction most of the time. And it gets smaller and smaller. And when x is positive, that number gets larger and larger. The 0 to the 0 is undefined, but when we redefine the function to be 0 at x equals 1, we said the limit as x approaches 0 actually is 1. So when we add that point, this function is continuous. And then we said, okay, let's compute the derivative by taking the log of both sides and using logarithmic differentiation. We found this to be the derivative. Isn't that pretty? We said the zeros of the derivative are the x values where the original function has relative extrema. So if we look at this, we see that the derivative has a 0 at this negative 0.637 or negative 0.367, sorry, and positive 0.367. We actually did the work analytically, and we said that that was plus or minus 1 divided by e. So let's type that in, 1 divided by e. We see that that's the same value that we get on here for the zeros of that f prime. And what else do we see? Just looking at this graph of f prime, we see that the derivative is positive from negative infinity to negative 1 over e. So that means the original function should be increasing, and it is. And then the original function, or the derivative, is negative from negative 1 over e to 0. So the original function is decreasing. And then the derivative is negative from 0 to positive 1 over e. So the original function is decreasing again. We also can sort of imagine that that function has a 0 slope, or an undefined slope, excuse me, at x equals 0, y equals 1. It looks like a tiny positive or a tiny negative slope to me. But according to our calculations, the derivative is undefined there. And we can also see from the derivative graph that it's undefined. So we've got a vertical tangent line there. But then to the right of x equals 1 over e, the y values are positive. So the original function is increasing. So that is consistent with all of our calculations and all of the work that we did by hand. The domain of f prime is all real numbers except x equals 0, as we can see from looking at the orange graph. And then if we want to, we can compute the tangent line of the original function at some point x naught. And then we can evaluate the derivative at that point. So at x naught equals 0.2, the slope is negative 2.69. Then we can graph the tangent line. The tangent line is given by the y value at x naught plus the derivative at x naught times x minus x naught. And you can see how that tangent line changes. You can see that we've got a slope that's very close to 0, near 0.36, or remember that was 1 over e. We get a tangent of 0, a tangent with a 0 slope there. And of course, that x value can change. So you can let the x change and see that the derivatives are negative there. And we've got a 0 slope at 1 over e. And then when we go to the right of 1 over e, those slopes are all positive. We can tell that they're positive by looking at the graph of f prime and also looking at the tangent line. It slopes up. As you look at it from left to right, the y values increase. And say y values decrease as you look at the tangent lines to the left of 1 over e, right? So here we've got negative slopes, then we have 0 slope at the bottom. And then we get small positive slope, and then the slopes get larger and larger and larger as the tangent line gets steeper and steeper and steeper. And then you can't see it anymore eventually because it's off the screen. That's between 0 and 5. You could also look at between -5 and 5. Draw some tangent lines there. So we've got small positive slopes. And then at the top, we have a 0 slope. That's at -1/e. Approximately -0.37. And then our slopes are negative here. And you say, what is the negative slope? At that point, it's actually negative 0.84. It's the change in y divided by change in x at that location. Okay. We said f prime is undefined at x equals 0 and 0 at plus or minus e. So we could label that on the derivative graph. We could label that on the original function. Since f prime is changing signs at 1/e and -1/e. Now we've got those relative extrema, as we've discussed. Now I've plotted a lot of points. I'm going to get rid of some of those. And let's get rid of the tangent line for a bit. All right, so that's f prime. And with this graph of f prime, we can see that the original function is increasing on the interval from -∞ to -1/e, decreasing from -1/e to 0, decreasing from 0 to 1/e, and then increasing from 1/e to infinity, which is consistent with the graph itself. Increasing, decreasing, decreasing, increasing. You can say, okay, I'm interested in points of inflection. So to find points of inflection, we look for, we look at f double prime and see when f double prime is 0. F double prime is 0 at this location, x equals -1. And f double prime is positive to the right of -1. So the graph is concave upward until we get to -1. And then it's concave downward between -1 and 0. And then it's concave upward again from 0 to infinity. So how do you know? Well, when the second derivative is positive, that's when the graph is concave upward. When the second derivative is negative, the graph is concave downward. So let's plot that point at -1, f of -1. So that is a point of inflection. So the purple points are points of inflection. Those two teal points are our relative extrema. And one thing I want you to notice is that the points of inflection corresponds to relative extrema of the derivative, with the exception of this one at x equals 0. You might say at x equals 0, we don't actually have a relative extrema, or we don't have a relative minimum for this first derivative because the first derivative isn't defined there. But the definition of a point of inflection is a point on the graph where the graph goes from concave upward to concave downward, and x equals 0, y equals 1 is a point on the graph where the graph goes from concave downward to concave upward. So where points of inflection are where the second derivative changes signs, so you're going from concave upward to concave downward, or vice versa, concave downward to concave upward. So technically 0, 1 is a point of inflection, even though f prime does not have an extreme value there. But notice one thing that we typically look for is we look for those relative extrema of the first derivative. So you say, where does the first derivative have a maximum? Well, it has a maximum at x equals -1. And so since the first derivative is increasing from -∞ to -1, the second derivative is positive from -∞ to -1. And since the first derivative is decreasing from -1 to 0, that means the second derivative is negative from -1 to 0. So the graph is concave downward. So we see that the second derivative and the first derivative are basically telling the same story. And we are able to use that to infer the intervals where the graph is concave upward or concave downward. So let's state that, and I think then we'll be done. We'll say the graph of f is concave upward on negative infinity to -1 and 0 to infinity, because the second derivative is positive on that interval and positive on that interval. And the graph of f is concave downward on a -1 to 0, since the second derivative is negative here. And we see that that's consistent with the graph. The original graph is concave downward from that first purple point, -1, 1, to that second purple point, 0, 1. That's it. That's our section project. I think it's kind of cool. Had to do some logarithmic differentiation. We got to explore some limits. We got to see a vertical tangent line at x equals 0, y equals 1. Lots of cool things. We have to do some curve sketching. So finding those intervals where the graph is increasing and decreasing, concave upward and concave downward as well.